Curves in industrial design. Non-uniform B-spline curves and their basis functions. A non-uniform B-spline is a B-spline curve for which its Bezier components are traversed in different amounts of time. In a non-uniform B-spline, the nodes of the node vector need not be equidistant. For example, the node vector 0, 0, 0, 0, 0.5, 2, 3, 3, 3, 3 corresponds to a non-uniform cubic B-spline composed of 3 Bezier pieces. The first Bezier component is parametrized by t between 0 and 0.5, the second by t between 0.5 and 2, and the third by t between 2 and 3. Since the basis functions depend on the node vector, they are different for uniform and non-uniform B-splines. They are shown below the basis functions for uniform and non-uniform node vectors. On the left, we have the uniform node vector and their corresponding basis functions, and on the right, we have the non-uniform node vector and their corresponding basis functions. These node vectors are equal except for the fourth entry, which is 1 in the uniform node vector and 0.5 in the non-uniform node vector. The basis functions are different. We can see that the first basis function of the uniform node vector is supported in the interval 0, 1, whereas the first basis function of the non-uniform node vector is supported in the interval 0, 0.5. The second basis functions are also different. We can see that the shape is very different, although they are both supported in the interval 0, 2. This is because 1 and 0.5 both belong to the interval 0, 2, and this affects the shape of these curves. The third, fourth, and fifth basis functions are also different, and only the last basis functions are equal. On the left of the screen, we see a B-spline curve composed of 3 Bezier components, which are in different color. H1 is the amount of time needed to traverse the first Bezier piece, H2 to traverse the second Bezier piece, and H3 to traverse the third Bezier piece. In this case, they are all equal, so the B-spline we have here is the uniform B-spline. Its node vector is here, and these are the basis functions that correspond to this uniform B-spline curve. If we look at the Bezier vertices of the control polygon, we see that C3 is the middle point in the interval defined by C2 and C4, and C6 is also the middle point in the interval defined by C5 and C7. We make H2 larger, meaning it takes longer to traverse the middle part, the middle piece of the B-spline curve. We see that the shape of the B-spline curve has changed. We do it again, so we can see the change of the shape of the curve, and also its node vector and the basis functions. If we look at the vertices of the Bezier control polygons, we see that the proportions have also changed. Now C3 is no longer the middle point in the interval C2 and C4. It's in a position that depends on the proportion given by H1, H2, and H3. And the same for the last vertices. If instead we make H2 smaller, the green middle part gets shorter and shorter and shorter and gets closer and closer and closer to the segment between D2 and D3. For a non-uniform B-spline, the shorter the basis function support is, the closer the curve gets to the corresponding control point. The shorter the segment of the curve affected by the basis function is. In summary, when a basis function has small support, the curve is closer to its control point, and that control point affects the position of the curve in a shorter interval of time. In SubCAD tools, to draw a B-spline curve, the designer can choose the vertices of the control polygon and the node vector to get a non-uniform B-spline. The number of entries in the node vector is related to the degree of the curve and the number of control points. For cubic B-splines, for n+1 control vertices, the node vector has n+5 entries. If the first 4 entries are equal, the cubic B-spline starts at the first vertex of the control polygon. If the last 4 entries are equal, the cubic B-spline ends at the last vertex of its control polygon.